So, this is part 2 of a story that started in basically a decade ago. At that time, Albert Sims and I started a study because we were tired of answering the question, why can't I have high protein and high yield? Basically, because you like both. In an ideal world, we would have 100 bushels at 14 pro. If we look at the conceptual model of how yield is formed and how protein is formed, and in a relationship to the amount of nitrogen you give it, there is basically 3 phases. One phase where initially grain yield increases more, then a phase where eventually grain yield starts to taper off, but grain protein continues to increase, and then a phase where yield no longer increases, but grain protein still increases almost linearly, and eventually that thing bends off also. Most of the time for us, we have a margin of safety built in all our recommendations to maximize grain yield, and then we try to push our crop to 14. So we're in this area between the top of B and somewhere in C. We try not to over-fertilize because we know that the crop will start to lodge. Too much N, we have a risk of increasing lodging. Okay, so the cost of grain fill. We also know that it takes more energy for the plant to make protein. So, and the third thing we know is that a lot of the starch is made during the grain fill period, where much of the protein, or actually the nitrogen for that protein, is actually taken up prior to grain fill period. So what the plant does is take up nitrogen earlier during the season, use it for other things, mostly an enzyme called ribisco, and eventually it will shuttle that, repurpose that nitrogen into the grain. So, this is an older illustration that I've used for years to show you that negative relationship between grain yield and grain protein. To say, well, it's harder for the plant to make protein than it is to make yield, and so we have this inverse relationship that as yields go up, grain protein goes down. That's how I showed it to you for years. And we tried to find those varieties that are in the middle and above the blue line that are what we call balanced varieties, a little bit of both. Okay. So finally, and this is what prompted the work in part, was NDSU and USDA HRS faculty in Fargo worked on introgressing what they called the high protein gene. It's called GPC-B1, grain protein content. B1 is then the chromosome on the short arm of chromosome B1, and it's called the GPC-B1 allele. And it supposedly is floating around in much of the NDSU material. And it was postulated to really increase basically nitrogen use efficiency, that more of the protein would end up in the grain. More of the nitrogen would end up in the grain as protein. But some later work that got published out of California, George Dukovsky said, well, there's also evidence that it will shorten the grain fill period, which is a little bit alarming, because I just told you that 80% of the starch that ends up in the kernel is produced during grain fill. So if you shorten that period, are we really increasing, or do we have a better use of nitrogen, or is it all about starch? So this is the original objectives from 10 years ago, and is the objectives of the second iteration of the same research. And then the question really is, can we manage with nitrogen those differences? Can we exploit the difference? Still problems?
Yeah.
Ah, shucks. We'll shut this off. Ooh, now I'm really loud.
You keep turning your head.
I keep turning my head. I'm a head father?
Yes.
Oh, okay, we'll try this one. So the first attempt. With Alvin and I, we had Fowler Sampson as high-yielding varieties. We had Glen Advantage as high-protein varieties. We had 4 rates of N, and we did a whole bunch of sampling. And we looked at the total amount of biomass, the nitrogen concentration in that tissue, and a whole bunch of things. A lot of work. And the result was that Fowler, in both absolute terms and in relative terms, was better at picking up nitrogen and shoveling it into the grain and making more starch. So overall, Glen, in contrast, did proportionally accumulate more nitrogen during grain fill, but in absolute terms, it couldn't beat Fowler. So that GPC1 B1 allele supposedly promoted stability and made that plant more efficient and stay around longer during the grain fill period. And that's, in the greenhouse, would result in higher protein content because the plants would just keep chugging longer. But the way it worked out in the field was basically that N didn't get shuffled into the grain. So it was lost for grain protein content. So, high-yielding varieties, Fowler, appeared to be able to remobilize as well as produce more starch and more protein. Only when we had really cool conditions did Glen kind of do its thing. So, and the N management of different N rates didn't do anything for us. Basically, it came down, and you've heard me say this before, GPC1, and this, we thought Glen had GPC1, and then we got the marker data eventually back, and then it said Glen didn't. But so I can't say GPC B1 did it, but Glen is basically a lazy variety. And you've heard me say this before. High protein varieties seem to be just lazy compared to varieties like Fowler that do everything better. Both in the amount of starch they produce, the amount of N that they take up, everything they appear to do better than Glen. So the high protein variety was just a lazy bugger. So, but because we found out that indeed Glen doesn't carry the marker, we started over. So Matt Rouse at the Cereal Disease Lab, GPC B1 allele is closely linked to, I believe, SR2, stem rust resistance 2. And so he made a bunch of backcross populations with 6 parents: Advanced, Bowles, Forefront, Lakeford, RBO7, and Saban. And we made this offspring, pool of offspring, where we tracked basically the presence now, particularly, of that GPC B1 allele. And so we made 2 backcross lines that had the allele, and 2 backcross lines where we knew for sure the GPC1 allele wasn't. And then we did, rather than 4 rates, we only did 3 rates at N. Below optimum, kind of optimum for the location, and then a extra shot, a high rate of N. And we chose Roseau, Crookston, and Brookings. In a way, we chose those locations so we had a gradient of potential growing conditions during the grain fill period. Because on average, Roseau should be a little bit cooler than Crookston, and Crookston should be a little bit cooler than Brookings. Now that's the gamble you take, and of course, last year we know all what happened. So rather than doing this really intensive sampling, we made it a little simpler, and we just looked at grain yield, grain protein yield of grain protein yield, which is those 2 multiplied, heading date, and physiological maturity. We're really focusing on whether or not that grain field period got shorter. Okay, so what happens? So first of all, it still becomes a very large experiment, 270 plots. We use what we call a split. So in block 1, you have the N rates applied at the large block,
Then you make a block of 5 plots here. Within those 5 plots, we would have the original parent, those 2 backcross lines that have GPC-B1, and 2 of them that didn't. And those last lines get randomized within that. And then if this was advanced, then this block would be bolts. It gives you the best precision to compare the lines within each parent. So the results, 2019, very quickly. If I average, I take the parent not in this consideration, just the backcross line. So those 2 lines with, those 2 lines without, averaged across the 6 backgrounds. Grain protein yield in Brookings, slightly higher, but then in Crookston and Roseau, about the same. Grain yield, same in Brookings, slightly lower in Crookston, and the same in Roseau. Grain protein, higher every single time when GPC1 is present. So that makes you think, okay, it's a high protein gene. Then look at the grain fill period. Lower every single time. So then 2021, because in 20 we didn't do anything, we were all hiding in our basement for the whole summer. Brookings, grain protein yield same. Crookston, grain protein lower this time for GPC-B1, and again the same for Roseau. Grain yield lower each time. Grain protein higher each time. Unfortunately, we had a little miscommunication, and Carl didn't collect heading date and physiological. We did collect heading date, but not physiological maturity, so I can't calculate out the days for the grain fill period. Lower, lower. To me, there's no, and I didn't show you that data, there's no interaction for end rate with the presence of GPC-B1. At the lower rate, at the middle rate, and the high rate, all the varieties pretty much, there's a change in overall, but there's not a crossing line. There's no crossover interactions. Nothing is happening. So all the varieties, the cross varieties, seem to be the same. And N doesn't, presence of GPC-B1 doesn't change how the plant used the N. But the grain protein was higher when GPC-B1 allele was present in 6 out of the 6 site years. The grain fill period was more often shorter by the presence of GPC-B1 than not, 4 out of the 6 environments. And the grain yield more often was negatively affected by the presence of GPC-B1 allele than not, 4 out of 6 years. So basically, it confirms what we did already in a way, and what the data was with that initial study. So the grain protein yield seems to be less affected overall, where we have 1 year it's a little bit higher and 1 year where it's a little bit lower. And the other years, pretty much there is no statistical difference between GPC-B1 present and not present. So my interpretation, the GPC-B1 allele shortens the grain fill period. And we're simply diluting the amount of protein by less starch, resulting in a higher grain protein content. So basically it's a dud. Okay. So what does it all mean for you in the real world? Because this is a nice academic exercise and we can have all kinds of fun with it and the students love it. Not really. Well, what does it mean for you? So, I have a question for you. What is the difference in the amount of nitrogen taken up by the crop to increase grain protein by 1% for an 80 bushel crop? Ever did the math? Did you ever do the math? Is it 82 pounds of N? Is it 28 pounds of N? Is it 8.28 pounds of N? Or is it 2.82 pounds of N? See, I played with the numbers 2 and 8 here. Which one is it? A, B, C, or D? You have to give an answer or we're going to be here for a while.
B.
Raise your hands. B?
How many for B? How many for A? 1. How many for C? How many for D? Okay. Drum roll. It's C. It's only 8 pounds. That isn't very much, is it? Heck, we make more errors when we send a floater across the field. So, what are the sources of nitrogen that the crop has access to? Well, for different yields here, 40, 60, 80, and 100, if we follow the U of M recommendations, because it's a little easier math, because it's a simple formula, we take the soil nitrate test, we take the previous crop credit, we then have the applied amount, and we have the contribution of mineralization/deposition. Now, there's an old rule somewhere about for every single % of organic matter in this area, it's probably about 10 pounds, but it really varies from year to year because it's influenced by temperature, it's influenced by amount of water available, etc., etc. So, if we assume for each of these yield goals that the previous crop, the previous crop credit is going to stay the same, your soil nitrate test didn't change, and your mineralization is constant for a particular year, see how we have to start applying more and more nitrogen. Well, duh. But now convert that as a percentage of the total need. What do you see for a 100 bushel yield versus a 40 bushel yield? What is really the big difference there? For a 40 bushel crop, proportionally, the applied is a very small amount. And that amount gets larger and larger and larger. Okay? What's a different way to interpret that? Remember, we only need 8 pounds difference applied to get an increase in grain protein of 1%. It's a little bit of a twist. You have to think a little bit differently about it. But the one thing we don't have control over is mineralization, right? Everything else is pretty much known. As we're pushing yields up higher, the amount of slack in our system is less and less. So small differences in applied with higher yields, remember the floater and an error, has larger consequences. If we all of a sudden have a dry year and we don't have that 30 pounds of mineralization, we actually have 20 pounds of mineralization, all of a sudden those gaps get larger. Everybody with me on that one? So as we're pushing the envelope, we don't have as much wiggle room in our system. We don't have as much buffer left in the system. So, you know now that that plot that I started with, we don't use that anymore. I don't use it anymore. I now have this really magic graph with grain yield on the bottom, grain protein yield on the side, and a big red line. The big red line basically signifying 14% protein. Okay, and then varieties scattered all around that. So look at the numbers, and then I have a question for you. Which of the variety is more efficient with N? Bowls or trigger? Very high protein variety, very low protein variety. I'll go back to the numbers. Can you find them? There's bowls, there's trigger. Which one is more efficient with nitrogen?
Trigger.
Why?
More grain yield.
No, it has more grain yield, but it produces, both of them produce 620 pounds of protein per acre. So they shoveled an equal amount of nitrogen that they've taken up into the grain. I would argue they're equally good with the amount of nitrogen given. Okay, next question.
Which one is more efficient, 95-90 or roll-off? Both give about 14% protein. Here's roll-off, there's 95-90. Which one is now more efficient?
95-90.
95-90. It apparently was able to squeeze a hell of a lot more nitrogen because it has higher yield. It actually produces way more grain protein per acre. So GPCB1 is a dud. But there are varieties that manage nitrogen differently. And that's what this graph shows. The ones that are up the line do something better with nitrogen, because more of it ends up in the grain. Now, that was 2020 data. This is 2021 data. What do you see here? Well, everything all of a sudden is above 14. Huh. This is grain yield as a percent of the mean. It's not absolute yields, but everything is above 14. Now, if you looked at the scale, there's actually, last year, there's a bunch of varieties across these 8 locations that produced more grain protein last year on a per acre basis than they did the year before, in 20. So why do I have, and some of them are about the same, the scale is about the same here, most of them are within a couple of pounds of one another. So why is everybody above 14 again? They made less starch. They just diluted it with less starch. That's why we have higher proteins. So, take homes. I'm right on the dot, like a trained professional. Okay, GPCB1 is a dud. We're not going to look at it anymore. There are, however, differences for grain protein yield among the varieties. But the differences in final grain protein are driven more by final grain yield than they are driven by nitrogen management. We just have less slack buffer in the system as grain yields increase. So, and you're going to love me for this, can I apply less nitrogen on varieties that carry the GPC1 allele? No, I think it's a dud. The bottom question is much more important. How much N should I apply to hard-red spring wheat this spring? The price being around $1 a pound. Given what I just all told you now, my answer is fertilize for the crop you want, not for what you had last year. We cannot afford to cut back on nitrogen because it's not nitrogen that determines our final grain protein. It's the grain fill period and how much starch we produce that determines our final grain protein. And so, you know your ground best. We've had some recharge. If you think we're going to have an 80 bushel crop, you better fertilize for an 80 bushel crop, or you're going to be sorely disappointed in any variety. Now, 95-90 might do it a little bit better, but eventually, for every single point, it's not that much nitrogen. And if we don't apply for 80 bushels, we're going to get caught. That's it.
Are there any questions? A few minutes.
Yes,
So
Kyle.
that would be beyond the standard 2.5 pounds per...
No. So the 2.5 pounds is really, for us, still kind of solid. In Minnesota, and in a way, Dave Franson's, if you look at Dave Franson's recommendations, he has just more data overall, more nitrogen response curves. We cannot, in Minnesota, yet get to the same kind of recommendation where we take yield goal kind of out of it. And basically, that's your crop history, in a way, on those fields. In the way he has, medium, low, and high yielding conditions.
And we don't have enough data to say if you have a high protein variety, you can back off 10 pounds in his recommendations. When you do the backwards math in all of Dave's, you come out to very similar numbers. Remember, we have a margin of safety built in all our recommendations. Dave does too. That 2.5 is a very magic number. We cannot get away from that.